everybody, so this unit that we're going to start is called equilibrium. And you've done some equilibrium before, and this first part of the unit is a lot of review. There are some new parts to it that weren't mentioned last year, like for example, what K actually is derived from, and there are different types of Ks, for example, Kc and Kp. So let's get started on this. This particular slide presentation, you'll see a lot of the text is already in there. So as you're listening to me and you're looking at this and reading through it, I'm going to go a little bit quickly through this first part. So last chapter, what we were really interested in was how fast the reaction happens. In this chapter, what we're really looking at is the reaction's gone on for an infinite amount of time, and it's reached a certain state that we call equilibrium. And at this point in the reaction, the amount of products and the amount of reactants no longer change. They're sort of at this state where there's no longer a visible reaction occurring. And it's kind of weird because there is actually a reaction occurring. It's a reversible reaction. The reactants are becoming products, and the products are becoming reactants. They're going back and forth, and they're happening at equal rates. Now this happens maybe in minutes or hours or years. We don't really know. And we're not really interested in figuring out how quickly we get to equilibrium, although there are some questions on that. We're more interested in thinking about, well, we've reached equilibrium, what's going on? How much of the products and reactants do we have? And then the other thing that we're also interested in is, how can we disturb equilibrium? Sometimes we don't want to be at equilibrium in a system. We want to try and make more products. How can we do that? So a system at equilibrium, again, it's the point where the reactants and the products are remaining constant. They're not changing. And this is because we have equal rates, equal forward and reverse rates. And this implies that the reaction must be reversible. If the reaction is not reversible, we can't have a reverse reaction, and we can't reach equilibrium. Now again, this doesn't tell us anything about the actual rates. It just tells us, how much product to reactant we have. Now we can tell if we form more product that the initial rate was probably faster for the forward reaction, but beyond that, once we're at equilibrium, the rates are equal at that point. So again, with IB, they'll talk about the extent of a reaction. And by extent, they mean how much product is there, how much reactant is there. And we'll talk about, hey, it lies to the right, meaning that we've made a lot of products, or it lies to the left, meaning we have a lot of reactants. So again, we always talk about extent. This is the amount of product that's appeared after an unlimited amount of time has happened. So what are the types of equilibrium? Well, there are three types. Two main types, but they can be divided up further. We have physical equilibrium and chemical equilibrium. And within physical equilibrium, we'll talk about solution equilibrium and we'll talk about phase equilibrium. So physical equilibrium, we're not going to do much with in this chapter. We really don't talk about it. We mainly talk about physical equilibrium when we do solution equilibrium. And that has a special K, which you've heard, KSP, and this talks about, saturated solutions. And we'll do that chapter with acids and bases. Another type of equilibrium is the talking about vapor pressure. When we talk about vapor pressure, we talk about, gases condensing and liquids vaporizing and how the rates are equal. But what we're really going to focus on in this chapter, and all the problems are going to be based on chemical equilibrium. And this is where you have a reaction. It has products, it has reactant concentrations. They're not changing. We have forward and reverse rates that are equal. All the equilibrium that we deal with is dynamic. There's always changes going on. We just can't see them because the net change is zero. If they have an answer choice where it's, the reaction is stopped or the rates are zero, it's not true. So the big part and the key to understanding equilibrium mathematically is this law of mass action and the mass action expression. We also deal with something called a reaction quotient, which is where the system is not at equilibrium. Now, we've done rate laws, and so now we can really start to understand what's going on with equilibrium. Now, the scientists studying this, they take a really big leap. And we were talking about mechanisms last chapter. In this chapter, we don't deal with the mechanisms. And we essentially assume that all reactions occur in a single step. This allows us, if it's a reversible reaction, which it will be, to write a rate law for our reaction up here, where we set the rates equal to each other and their k values. Now look at what I do now. I'm going to rearrange this so that I can get k forward over k reverse on the left side. So I have kf equals kr. This is equal to NO2 squared, because we assume it's second order, over N2O4. And what we do is we make this kf over kr, KEQ. And it's equal to the products divided by the reactants. So that's what we have going on. We have the products over the reactants. But I'm going to pause for 1 second. This KEQ value, it's equal to the KF over the KR. That's how we're representing it. And this is equal to the products over the reactants. Raise their coefficients because that represents their orders of reaction. I know last year they'd be like, you just take the products and you raise them to their coefficients and you divide it by the reactants. This is why. Because it's based on the rates being equal and the rate laws setting equal to each other, solving for the k's, and those rate law constants become the KEQ. Now, just like a rate law constant, you can't change it unless you change the temperature. And what ends up happening is we call this the law of mass action. And basically what this says is that if you have a specific temperature, you will have a situation where the products over the reactants, that ratio at that specific temperature, will always be held at the same number. It won't change. You'll have the same equilibrium constant unless you change the temperature. Now there's something called reaction quotient, and they use the symbol Q. And Q is equal to the products over the reactants. The only difference between Q and KEQ is that Q is just not at equilibrium. The reaction will continue to change. You'll continue to generate products or reactants until you reach equilibrium. And at that point, when you are at equilibrium, that is when KEQ will be equal to Q, and you'll be at equilibrium, where Q will no longer be Q, it'll be K. Okay, so look, things get a little tad bit more complicated because KEQ is referred to as either KC or KP. You'll very rarely see the AP exam use KEQ, they'll use KC, they'll use KP. C stands for concentration, P stands for pressure. So we could have a KC, they'll use concentration, they'll have a KP, it will be pressure. With KC, we use brackets, and then the exponent up here. With KP, we'll use the symbol P for pressure. We'll show the symbol of the element, let's say it's hydrogen, and then if it's squared, we'll put a 2 around it in parentheses. So it's important that you don't put brackets when you're talking about KP. Remember, when you're not at equilibrium, you'll use Q, you won't use KEQ. Also remember that KEQ and Q, they will look identical until Q equals K. Now, the meaning of K, and some important things about K that I'll talk to on the next slide here. If K is really large, you might remember, products are going to be greater than reactants. We're going to have a greater concentration of products than reactants, greater pressure than reactants. If K is really small, less than 1, it means that the reactants are favored, and the reactant concentration will be greater than products. If K is equal to 1, then this is a rare situation where products equal reactants. I know the Regents loves to ask, hey, what's true at equilibrium? Products equal reactants is one of the choices. But they'll always put in the word always, which is always true. And that's not always true. It's possible. The AP exam actually had a question. The products were equal to the reactants. The K was 1. I think people, were like, what? But they were trying to mess with you. It can be equal to 1. It's just not common. Now, Something nice about this, I'm sure some of you will be happy, there's no units for Kp, Kc, Q. All the units are compared to a standard, and so when they compare them to that standard, they cancel out all of the units. Okay, when we think about forward and reverse reactions, so if you're analyzing the reverse reaction for KEQ, then you need to take the inverse. Remember with delta H, when we dealt with that, we negated it. Well, in this case, we take the reciprocal. Because if we have a KEQ, it will be equal to products divided by reactants. If we reverse them and we make the reactants the products, we make an opposite or a reciprocal reaction, our KEQ will be equal to reactants over products. And this will be 1 over KEQ at that point. Remember, with the Ks, we do not include solids or liquids. Their concentrations will remain constant. They will not change. We're only interested in analyzing things like gases and aqueous. Those are the only types of substances where we will have a change in concentration that's measurable. Now, when you have a system at equilibrium with different phases, they call it heterogeneous. In this chapter, we're mainly dealing with gases. We're dealing with homogeneous equilibrium. One last thing that I want to talk to you about for this video is relating Kc and Kp. Well, you can relate it through the gas laws. And here's what the relationship looks like. Kp is equal to Kc times, in parentheses, RT. R is the gas constant, 0.0821. K is the Kelvin temperature. And delta N is the change in moles of gas. And what I mean by that is it is the moles of product gas minus the moles of reactant gas. Now, what kind of problems do you see with this? Well, you see problems where they ask you to, analyze the meaning of K. Is it small or large? What's the meaning of the K? How does it tell us about what's favored or what's going on in the reaction? That is the first thing. The second thing is they will manipulate K. So they will have it where they, change the coefficients or they reverse the reaction, and they'll ask you how K changes. And that is the second type of problem that we'll see. So in class, we'll focus on those things and we'll practice that. Our next slide presentation will be problems using ice tables, which you may remember from last year. So we'll do those again. All right, thanks so much for watching, and I hope that you learned something new about equilibrium, and I'll see you soon.